Okay, what we have here is a problem where we're calculating work. We're going to do this with a known force and some information about the angle that the force is applied and the angle of the displacement vector. All right, so let's take a look at what the problem is asking us. We're given a block of 3.8 kilograms that's pushed along a surface that has a coefficient of friction. We're not told that coefficient of friction. The block is pushed a distance of 1.9 meters, and the magnitude of the pushing force is given as well as the angle below the horizontal. And we're told that the block starts in motion, which makes sense because we are asked for a kinetic coefficient of friction. We're given the initial velocity. And we're asked how much work must friction do in the block for the final velocity to be equal to the initial velocity. Okay. So what we have then is, since the initial velocity is equal to the final velocity and the work energy theorem, so we'll say that gives us that the net work is equal to the change in kinetic energy. So here, the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared equals 0, because v final equals v initial. Thus, the net work is 0. Okay, so that's going to be information that will help us solve the problem, because in other words, if we know that, so this tells us that the work done by friction plus the work done by pushing equals 0. They have to sum to 0 because there's only two works and two forces. We could get this same result if we thought about the sum of forces in X. So the sum of forces in X, which would be F cosine theta minus F friction equals 0. Okay, that's just telling us that those forces have to be equal, and if the forces have to be equal and the distance is, then the works are equal but opposite in direction. So just like the forces point in opposite directions, the works, although not being vectors and thus not pointing in opposite directions, do have opposite signs. Okay, and then we can see that if we take a look, for example, here at the work of pushing. Okay, now the work of pushing is actually easier to calculate. I'll sort of set up both, but I'll continue with the work of pushing. So it would just be the force of pushing, okay, which we'll just call F as before, times cosine theta. All right, and basically what I'm doing there is I'm just taking the magnitude of the x component of force. Well, that's the parallel force to the displacement. Okay, and so that multiplied by d, and I'll say that that is the same as F dotted with d, because if we were to take the force product, the dot product, we would just get the pushing force, the displacement, and the angle between the two, well, cosine of the angle between the two, which is just cosine theta again. So it's the same thing, different order. Okay, and then if we take a look at the work done by friction, well, that is going to equal the friction force dotted, we'll start just with the definition, with the displacement. Okay, well, the direction of the friction force is going to be exactly anti-parallel to the displacement, so that what that's going to look like is F friction times d, because they're both scalars now, no vector notation, and then cosine of the angle between them, which is 180 degrees. Okay, and so then it's just negative force of friction times distance, displacement, magnitude. Okay, but then what's the force of friction? Well, to calculate the force of friction, we can't assume that the normal force is just equal to the gravitational force of the block, because, well, if you think about the forces in the y direction, there's not just two of them. So if we want to find the force of friction, well, the force of friction is going to be mu k Fn, mu k, because we have a block in motion. Okay, and then what do we know about Fn? Well, we have the sum of forces in y is going to be Fn minus F sine theta, which is the y component of the pushing force, minus mg, and it's going to equal 0, which gives us that the normal force is equal to mg plus F sine theta, which makes sense because it's greater than it would be otherwise because some of the force is pushing the block down into the table. Okay, and so then the work of friction is just going to be mg mu k mg plus F sine theta, all multiplied by displacement. Okay, so we got our two work expressions for the work of friction and the work of pushing. If we go back up here, so I'll point out that we could have actually just stopped at the work of pushing because we know that the work of pushing has to be equal to negative of the work of friction. And so you can see now why I said, well, it's harder to calculate this one. It just takes extra steps. So if we were only asked for the magnitude of the work of friction over here, we know that we can just simply find this magnitude and then put a negative in front of it. I went ahead and showed where the work of friction, how the work of friction is calculated, because it'll be helpful for the next couple of steps of the problem, as well as being good to see how to do. So, okay, when we actually plug in numbers, I'm going to go ahead and plug them in this way and say that the work of friction is just going to be equal to negative times the force, which is 1.24. Okay. So, all right, negative times 1.24 newtons, and then we have the distance, which is 1.9 meters, and then cosine of the angle 36. All right, so let's calculate this over here. So negative 1.24 times 1.9 times cosine of 36. All right. So it looks like that we get under a joule. All right, does that make sense? Yeah, I mean we have something that's only has 1.24 newtons of pushing force. Yep. Okay. Let's make sure that I'm in the right mode. Nope. That's the issue. Okay. That's why the force was too small. Okay, so let's go back and recalculate this. Or not the force, but the number of joules. Okay, so negative 1.9 joules. Okay. Excellent. 0.91 joules. Okay, so that's the work done by friction. Second part of the problem asks for what is the net work done on the block? Well, we already know that that's going to be 0 from the work energy theorem. Okay. All right, and as far as questions C, or part C, what must be the friction coefficient between the block and the surface? Okay, so if we're going to look there at the friction coefficient, okay, then we'll go back up to the expression that we had here for the work of friction, and we'll just solve for the friction coefficient. Okay, so I'm going to have then that the friction coefficient is going to be the work of friction divided by d, right, times mg plus F sine theta. Okay, and all of this is in the denominator. Okay, so we'll go ahead then and find that value. Okay, and as far as the the magnitude here, this expression right here for the work of friction is actually ignoring the negative, so it should be corrected if we're going to, right, because it has to be pointing in the opposite direction. Okay. But regardless of the negative, we'll take the absolute value of the expression to find the friction coefficient, which is not going to be a negative value. And okay, so if we go ahead and plug that in, right, then we're going to have our 1.91 joules. Okay, that'll be in the numerator. then divided by our 1.9 meters, multiplied by the mass, which was 3.6, I believe, or 3.8. Times gravity, our pushing force, and sine, the vertical component of our angle. Okay. So if we enter that value, all right, we're going to have this expression. Okay. So there we go. All right. And let's clear up that negative. Okay. Okay, so there is our friction coefficient, a small one, but to be expected because there's a very small pushing force that maintains a constant velocity. All right. So there we have a problem with work and friction and no acceleration, but the pushing force is at an angle. So we got to see how work bridges concepts that we saw with free body diagrams and concepts that we're beginning to see with energy. Thank you.